Hi, everybody. Welcome back to the episode on powder manufacturing. I have Paul Davis on board, and last episode we talked about different ways of manufacturing powders. Today we'll dig deeper into the gas atomization technologies, and we'll also talk about some of the obstacles because there are some obstacles. I have some evidence here that it's not always that easy to manufacture powder. But Paul will also come into that. He's very open and it's extremely informative. So stay tuned and see the entire episode. Thank you.
But now I'll move on to vacuum inert gas atomizing. So here you can see the top of the atomizing chamber. It is, of course, under vacuum, so it's a metallurgically clean process. Indo relatively unique in the fact that they can make fine powders for MIM. So there's not, I don't believe there are any other companies, or few at least, that can make vacuum atomized fine powder, which is an advantage for certain alloys, like nickel superalloys and aerospace and medical materials as well. Schematic of the atomizing process. In this case, it's a top pouring induction furnace into a tun dish and then atomized using different gases, as you can see here. So often the tun dish then is free falling into a free fall atomizer. We generally use confined atomizers to make finer powder, I would say. And that's the kind of scale as the plant, as you saw earlier in the video. This is actually an electrode inert atomizing process. So in this case, the bar comes down from the top, is melted in a induction coil. Yeah, absolutely. And that induction coil, interestingly, is copper, hollow because it's water cooled, and is actually 3D printed as well. So we're using 3D printing to make powders for 3D printing applications. And electrode inert gas atomizing tend to be free fall atomizers, especially for titanium alloys. So there's a refractory free process in effect. And again, producing very beautiful spherical powders.
I remember when I was working with atomization, we were working with some alloys that had high tendency of clogging in the ceramic nozzle. So therefore, instead of going to a very high superheat, we looked into the possibility of adding an induction coil around the tip of the nozzle to avoid it from clogging.
Yeah, absolutely. Depending on the alloy and its alloy constituents, so clogging can be a problem. So for instance, if you're using nitrogen gas, you can create nitrides, or if it's a sensitive alloy from oxides point of view, then you can get a buildup of oxides in the nozzle. And actually, the configuration of the nozzle itself is complicated, and the pressures, temperatures of the gas as well have an influence on the pressure just below the nozzle, and that can be negative. So it's actually blowing the molten material back up into the into the molten chamber if you're not careful. And depending on especially for finer powder, you want to really have higher pressures, higher temperatures, and as highlighted here. So we can manufacture fine powders or mid-size or coarse powder, and they all have their kind of challenges, I suppose. But of course, it's really creating the appropriate atomizing configuration and process parameters to make powders for metal injection molding or binder jet printing or laser powder bed fusion, powder bed fusion for electron beam or DED as well. So looking at you have to really set your atomizing geometry and process parameters then to target the right market that we're involved in. And generally, Indomim are interested in fine powder for MIM, binder jet, powder bed fusion, and then eventually we'll adjust atomizers to create powders, coarser powders as well for DD, E-beam, and HIP as well.
Yeah.
So it all, yeah.
Yeah, I have a funny thing about this. Very often I hear the powder producers saying, but the reason why the powder prices are so high is that we make this kind of powder, but you only want that.
Well, that's a good point about the
Yeah.
yield. Absolutely, and that's really why you have to configure your atomizer, which has a lot of variables.
Yeah.
It's the melt temperature of the molten material. It's the height, the metallostatic height above the nozzle.
Yeah.
And then the configuration of the atomizer itself, the protrusion of the nozzle, the angles and sizes of the nozzles, of course the gas temperature, its pressure, type of gas, all have an influence, and ultimately to create the molten material into both eventually sheets, ligaments, ellipsoids. Sometimes it's packets of molten material which then create fine powders, and creating finer powders is probably the biggest challenge. Ultimately, it's about the energy efficiency of allowing that molten material to stay molten along for it to get secondary atomization, and that's often very important. And of course, if you get your gas to metal flow rates wrong, you can end up with either nozzle blocking or nozzles blocking because you get a low pressure void beneath the nozzle, and then it can effectively just close off and freeze, and then you have to remove the nozzle, remove the tundish, and start again. Or you can result in flakes and needles and also satellited particles as well. So Indomim introduced a secondary ring of gas below the primary atomization to limit the recirculation, actually, and this seemed to be very effective at preventing recirculation. And that allowed the powder particles to form satellite free, which of course can affect its flow characteristics, which are pretty important for certain applications like laser powder bed fusion and binder jet printing in particular.
So is it because the powder, when you atomize it, goes into the chamber, but then when it goes around and it goes back in the chamber? Is that what you mean? You have a secondary ring to protect this backflush?
Exactly. So these particles, depending on the process gases, can recirculate and float around, and eventually, because they're solid and often very fine, they can end up solidifying on the surface of larger particles, which is why you can see some of the larger particles have kind of little satellites attached, because they basically stuck to the surface as it was solidifying. So having a narrow, finer distribution can help solve that problem. But yes, also having additional processes like this secondary anti-satelliting gas ring can help to avoid that and blow the fines to the side of the chamber and where they're down and then collected.
Stay away.
Exactly. And of course, adjusting the pressure of the gas can have an influence on recirculation. And here, what I've introduced a picture here from research that's highlighting simulation of computational fluid dynamics. So of course, as I mentioned, the variables involved in gas atomizing are complicated. There is a synergy with rocketry in effect, because we're talking about high pressure gases, as you see up to here, 80 bar, and then you form in shock waves because there's supersonic gases.
Yeah, you can see the shock waves at the last three of them.
Exactly. So there's a number of different shock waves forming, and no doubt a dead zone just below the atomizing tip as well, and that can have an influence on the drawing of the molten material into the atomizer. So you want it to be effectively sucked into the atomizer and then they're fragmented and atomized. So controlling the gas and modeling different atomization designs has now become a little easier by using computational dynamics modeling, as you see here. So you can model the gas, and then if you get perhaps even more complicated by modeling the gas as well as its interaction with the molten material. So you have two-phase computational fluid dynamics, and that takes a lot of computer power. But certainly it can yield very good results and trends towards different size distributions, narrow distributions, or finer distributions, for instance.
And when it goes red, you go to 700 meter per second.
Exactly. So
that's Mach 2.
Exactly. So it's going very fast. So the pressure has an influence on its speed, and ultimately governed by the classic formula PV equals nRT. So pressure, volume, and temperature have this basic relationship. But then you can, of course, adjust the geometries of the atomizer. And one obvious thing to do, perhaps, or not so obvious, is to include a bit of swirl, a bit of angular momentum to the atomizing gas, and that can have an interesting effect on the how the gas interacts with the molten material. So you can see here that the gas flowing through the atomizer and the molten material coming out, and then with and without the metal flowing can have an influence on the gas flows, and that's very important. So often in gas atomizing is getting the atomization to start, and then it generally it becomes stable, and you can even listen to atomizers literally to see how stable they are and become, and provide a bit of feedback loop on that as well.
I could imagine when you run Mach 2, it's pretty noisy. You're breaking the sound wall.
Yeah, absolutely. So yeah, of course you have to have your hearing protection on, but it is muffled within the chamber, so that does help, and there's a water jacket as well, which helps stop that sound transmitting so effectively. So that's good to have a cooled atomizing chamber actually from that aspect as well. So yeah, a bit of swirl in the gas is interesting, and then of course we talked about the speed. The die gas temperature can have an influence on the velocity as well, and basically the relationship that has been found more than 20 years ago, actually from 2004, was that as you increase the gas temperature up to 500 degrees, for instance, then the velocity of the gas increases as well, and that was basically found to reduce the average size, or the median, the D50 of the powder particles. So in this case, you can see that the D50 went from 20 micron down to 15 micron, and also increased the yield of fine powders as well. And similar work has been done also here, increasing the gas temperature from 293 Kelvin up to 573, and then the median particle dropped from 53.9 microns down to 38.06 microns.
And the gas to metal ratio, is that on weight or is it on volume?
Good question. I'd have to read this paper here, but it's usually volume, I would have thought, because it's
because it seems that you get a better yield with less gas consumption.
Exactly, and that's the economics of it is also important. At some point, you will tend to, the cost of heating gas will versus the consumption. The higher the temperature, the faster the velocity, so you don't need as much. So you can reduce your gas consumption, or you can just go as fast and as high pressure as you can, for instance. But at some point, there will be a kind of cost element of heating gas, and also the technology involved there is not without its issues. And it will become a kind of at a point where the return is not so good. So there's probably an optimum, and there are atomizers you can buy off the shelf now, which for laser powder bed fusion tend to heat the gas between 300 and 150 degrees C, for instance, to produce a 30 micron average size, which is bang in the middle of 15 to 53 microns. Fortunately, the shape of the powder doesn't seem to be affected by gas temperature. Here you can see the sphericity versus particle diameter. Often quite a nice trend, though, is the finer you get, the more spherical they become. I guess it's because they freeze quite quickly and the surface tension is higher. But the gas temperature doesn't really affect the shape, it seems. And then more recently, some new innovations are going on, manufacturing oxide dispersion strengthened steels. These are steels that have been earmarked for use in the nuclear industry, for instance, as raw materials, because their mechanical properties are excellent. But scaling,
and it's also for creep resistance.
Exactly, creep resistance. However, they haven't scaled as quickly as they could, but mainly because of the kind of trying to capture the oxides and make them equally distributed, and it becomes a challenge. However, there's a number of researchers in North America from universities and Ames Laboratory, for instance, who started using atomization process and introducing oxygen rather, into the atomizing gas and what that does, it's a kind of it reacts with the chrome to form a nice chrome-rich oxide on the surface, and then the oxides which react with yttria are trapped inside the particles. So it provides a nice a pool of oxides for manufacturing by additive manufacturing. This is quite a relatively new concept of passivation of powder particles, especially from an oxide dispersion strengthening point of view. And it seems prevalent in other materials as well. So, for instance, aging steels and even stainless steels, as printed by laser powder bed fusion, tend to have higher mechanical properties than wrought materials until they're annealed. And this is often due to oxide dispersion and strengthening aspects, actually.
Here you name yttria as a doping element to enhance the ODS. Do you know other elements that work for that? Could you use neodymium or niobium or things like that?
Yes. So in the aging steels, it's titanium and aluminium are present in the alloys, and they do form fine oxides, actually. And they can be controlled in terms of their size and distribution to enhance the material properties. I think oxide dispersion strengthening of alloys, especially for additive manufacturing, is going to be a growth area. And if we consider the new nickel-based alloy from NASA, it is an oxide dispersion strengthened alloy that's going to be used in their new rocket engines. Right, just finishing off on sustainability. There was a recent report on sustainability related to the specific energy of metal AM and the feedstock, which of course is the metal powder. And in this case, they published a table related to the different gases that are available commercially: argon, helium, and nitrogen. And the research found that if they produce powders with a 20 micron average size, with a 70% efficiency for induction melting, if they make different alloys like stainless steels, aluminium alloys, or Inconel 718, then they actually found that helium would be the most effective gas compared to argon and then compared to nitrogen. But then it's probably worth caveating that of course the cost of the gas has to be taken into account. Helium, more expensive than argon, more expensive than nitrogen, and helium not a very sustainable gas. It's an element that's formed from the radioactive decay of uranium in the core of the Earth, which creates alpha particle radiation, which effectively is fast-moving helium. Eventually, that slows down and gets trapped in oil and gas reserves, of which where most helium is extracted. But because it's a very light element, it will eventually float off into space, unfortunately. So it's not the most sustainable. And every time you pop a balloon, just think, oh, that's gone forever.
Forever.
Exactly. Unless you go to the moon, as you mentioned earlier. However, argon has its place being a noble gas, so it's very good for atomizing reactive or sensitive alloys like titanium. And then nitrogen, of course, dominates powder production because it's an air product ultimately and readily available and sustainable from that point of view if you use kind of green energy to produce it. I briefly mentioned rocket alloys, and I'll finish off with perhaps an example of.
If you jump back to this with the, because I have a question, because my understanding of it is that the heat capacity is different. So helium has the highest heat capacity of these, so therefore you can atomize more. You can get the heat out of the metal easier with helium, and that's why you see this number. Is that the right way of thinking?
Yeah, I think there's a number of aspects to the gases actually. Helium, which is effectively a molecule, though, of course, it's got more protons and neutrons, I suppose. And then nitrogen, which is a molecule, N2, typically. And then argon, which is effectively a monatomic gas. So there is a kind of atomic cross section. There's a atomic weight. There's a kinetic energy associated with that then as well. So yeah, like in cold spray, helium is the best gas for imparting energy into the molten particles, and I think the same principle applies to gas atomizing as well. I think nitrogen's the only molecule. The others are monatomic. I think.
They are.
There we go. And as I mentioned, what are the synergy with rocketry with gas atomization? Well, of course, rockets are all about energy conversion, maximizing the thrust or the velocity of the gas you're emitting. There's converging, diverging nozzles, which are used in gas atomizing. There's pumping and mixing of liquids and gas. Certainly low temperatures and very high temperatures. Supersonic gas jets, high performance materials. These new rocket engines are actually cooled nozzle jackets, so the fuel is used to cool the rocket nozzle itself prior to combustion, and of course these are now printed by additive manufacturing. So I wouldn't be surprised in the future that these concepts of rocketry, including the capabilities of additive manufacturing, producing complex internal structures, which could be applied to atomizing blocks and nozzles, are used in the next generation of atomizers going forward.
I have a little anecdote. We used to say when back in the time when I was atomizing that people living in windy areas are the best for atomization, because who now we talk men, but who has not tried to pee against the wind and learned the bad things about atomization?
Absolutely, yeah. It's all about the nozzle, I imagine. Anyway,
Yeah.
anyway, yeah. So just summarizing the presentation now. So of
Mm.
course, metal powder production has a long and established history. There's a wide range of different production processes available, producing powders with different morphologies, different size distributions, different characteristics, and ultimately creating a versatile and sustainable raw material that can be used in several different manufacturing processes, including metal injection molding and additive manufacturing. So that finishes all the slides I have. So now
Yeah.
what I'll do is I'll stop sharing, and we can, yeah, if there are any final questions you have,
Yeah,
I'm
I
open
have
to.
several.
Okay.
I would like to take a dive into this clogging of the nozzles.
Right.
Uh, because I remember when I was atomizing, we had issues with aluminum oxide, and I grew up in the traditional steel mill. And to kill the steel, typically when you have steel air melted, it's in equilibrium with the air. So you have oxygen in the melt. And when you cool it down, the oxygen wants to get out. And it can go out in two ways. It can find something to react with, or it can evaporate. And if it evaporates, it starts to boil. So when you typically pour into a ton dish, temperature can easily drop 100 degrees C, and thereby it starts to boil. In order to avoid boiling, you kill it by adding aluminium. But when we did that prior to atomization, we realized that the nozzles were starting to clog because the aluminium oxide is like chewing gum on hot asphalt. It sticks.
Sticks, yeah.
Yeah. Is that also something you have experienced?
Yes. So clogging of nozzles is probably the bane of atomization, as you said. But
Mm,
and from a melting point of view,
mm,
you absolutely. So killing the steel with pure aluminium, sometimes as bars or sometimes as pellets,
mhm.
is very important for most steel making processes. Actually,
Yeah.
absolutely.
Yeah.
So then you allow the aluminium to react with the oxygen to form alumina in effect.
Mhm.
And then it's how do you remove it? Well, in classic steel making, you would introduce calcium and
Yeah.
deslagging agents, and the
Exactly.
calcium reacts with alumina to
Mhm.
form a liquid, and then effectively just floats to the surface.
Mm.
And then you can remove it in an open air situation. You
Yeah.
literally remove it by hand.
Mm.
So having appropriate deslagging materials is important. Sometimes you can use wire feeders to
Mhm.
drive a clad wire into the molten material,
Yeah.
and then it dissolves the calcium as you go. And you can add
Mhm.
small additions as well,
Yeah.
more aluminium or more titanium as well potentially.
Mm.
So yeah, but then of course deslagging processes are very important, and can become a challenge for depending on the alloy. So for
Mm.
instance, nickel-free stainless steels, smoky, they
Yeah.
form a lot of slags. Sometimes the
Yeah.
slag can be protective as well,
Yeah.
however.
It's a
So
manganese based or high
exactly,
manganese
it's
steel.
high manganese. So
Mm.
you're replacing the nickel with manganese up to about 11%.
Yeah.
So it can be pretty high, and you need a lot of nitrogen as well to make it non-magnetic
Yeah.
ultimately. So it's about controlling the melt surface as well then, and the slag material can be protective in a way as well,
Mhm.
and there's a lot of skill to do that, and yes, in the UK and the atomizers in South Wales are probably world class in that regard. However, if you consider the safety aspects of melting metals in open air, then,
Mm.
as you said, the oxygen will react, but it can also react with carbon. So if you have alloys with high carbon contents, then you can form gases of carbon dioxide, carbon monoxide, which, as you said, can bubble, and then you can get a carbon boil, which is very hazardous. As you can imagine, the molten material can come out the top.
It creates foam.
Creates a foam, but it can also kind of spurt out, which can be dangerous when you're deslagging by hand. So that's an issue. The worst risk, of course, is the induction furnaces often have induction coils which are copper cooled with water. If the refractory should fail, and often they're either solid refractories or powder-based refractories, fritted linings, they can be a little safer because they kind of self-heal. But of course, if the molten material does interact with the copper coil, melt the coil, a water molten material reaction is catastrophic and can result in the molten material boiling and then ejecting from the furnace, and that's particularly dangerous. But there are many safety protocols in place, including sensors and electric circuits as well, to highlight if there's risks at all. Therefore, if you can avoid melting in air, probably a lot safer, because melting under a vacuum you're limiting how much oxygen the melt's absorbing. You can control it from that point of view, and probably a much safer, more passive form of melting and therefore atomization. So the safety is certainly, I would say, better when it comes to vacuum melting than melting in an open air situation. And then ultimately, if you can avoid melting large quantities of material altogether, then electrode inert gas atomizing is a very efficient process, because you're only melting a small amount of material that you need to atomize at any one time. And you can make them both batch and almost semi-continuous processes by feeding bar continuously. Absolutely. So yeah, perhaps from an economic point of view, then the electrode process could well be more sustainable. Of course, you do need to have the appropriate electrodes available. So you can't have perhaps the alloying capabilities and flexibility that you get with induction melting. But for basic materials, and if you consider MIM and additive manufacturing, most of these processes use international standards available as bar stock in any case.
Then I have a last question. It's on this sustainability. When you melt, you typically have the choice to take scrap or virgin material. What are the proportions typically in gas atomization? Can you go 100% recycled material, or do you have a certain portion of virgin material?
It is possible to get close to 100%. I think it probably the highest level is about, for instance, if you take a standard 316L stainless steel used in metal injection molding and additive manufacturing, the recycled contents can be up to 80%. And then there's a degree of refinement depending on adjustments to composition. So if, for instance, if it's for metal injection molding, you want to have perhaps a lower nickel content within the range of 10 to 11%. But if you want to make sure it's completely non-magnetic, then perhaps push that nickel content up to 14, so the top limit. So there is a degree of trimming and refining prior to atomization, and that can be about the last 20%. But it is possible to have melting practices which are like heal and pour, so you never pour out all of the molten material, and then you can backfill with and remelt scrap components. So for instance, these could be out of specification metal injection molded components or 3D printed components, and also reverted powder as well. We heard earlier about the different size fractions for the different markets. Ideally, you want to sell all of the different fractions for different markets, but if you can't, then having the ability to remelt the powder is very important. Although you do lose value, but you do retain the metal value at least.
Yeah. Perfect. Thank you.
Yeah, just highlight some different types of powders here. So here there's some fine copper powder with some good flow characteristics. That was made in South Wales actually, and then some fine metal injection molded powders as well. This is a little more sticky. Typically,
it doesn't flow at all.
Doesn't flow so well, no. But there are certain processes you can do to improve it. But yeah, so the size, the morphology, all have influence on the characteristics of the powder, and that's very important. So yes, thank you for inviting me for this talk. It's been a pleasure, and yeah, I look forward to our further editions.
Perfect. Thank you very much, Paul. I really enjoyed it, and I'm not lying, but I learned something new today.
Glad. Thank you.
Wonderful. Thank you very much. See you.
Bye.
Bye. Thank you for following this part 2 of the episode on metal powder production. In this episode, we just learned a lot about gas atomization and what is possible and where you have problems doing it. I really like Paul's explanation about the clogging and going deeper into what could go wrong in gas atomization and in the melting technology, because it really gives an understanding on why powder comes at a cost. So I hope you bring this with you in your daily life and have a better understanding on what it is you're doing when you buy powder for your 3D print technology or your metal injection molding components or your standard metal powder parts. If you like this podcast, I will be very happy if you'll subscribe and follow it, because I have more than 40 previous episodes out there with high-level experts going through different topics of metallurgy. And I have a pipeline with new experts lined up, ready to share their knowledge with you. So I really hope you will join the community and learn about metallurgy with all of us. So thank you.